buongiorno, buongiorno, my fellow students, for another episode of Physics. This is Mr. Finn coming at you from neighborly Northville. I have donned a new hat today. We are no longer the Gong Show, simply just the Michigan High School Baseball Coaches Association hat. So, hopefully everybody's okay. Hope you had a great weekend. Just going to touch base with parallel circuits today, and I'm going to review the series circuit Google form from last week. So we have all the answers going forward into this week. We're going to need those as we go. As you'll recall, those Google form questions were actually the homework questions. So those of you guys who are doing the homework, hopefully you're getting to see some of those questions a little bit before you have to answer them on a Google form. Okay. Reiterating, the office hours are going to precede the Google Meet hours. So if anybody has anything they wanted to address specifically, just don't want to be part of the group, or maybe a parent wants to email in, good time I'll be available will be those 30 minutes right before our Google Meets on Tuesdays and Wednesdays. Now remember, Tuesdays in the early AM or the AM first hour, in the PM second hour, Wednesdays in the AM third hour, and the PM fourth hour. Okay, guys, hopefully that's okay for you. Rotation work will be graded and moved into MyStar. So as soon as that's done, it might be done by now. But we're going to let that play out a little, and I'll make sure I keep you guys updated as to your grades on Google Classroom. I don't know how the ultimate thing's going to pan out, but it sounds like we're headed to a credit, no credit situation. But if you guys want, I'll keep track of your Google Classroom grades, and that way anybody who's applying to schools can actually see maybe there was extra work done in this class that's more indicative of something that's not credit, no credit. But I'll leave that to you guys as you move forward. So right after this intro, I'm going to show you guys the series stuff, and then we're going to move into the parallel stuff. Remember, we introduced parallel circuits last week, and I want to make sure I give you the lab example or a concrete example so you guys can see what we were dealing with in terms of parallel circuits. Okay? All right, let's head to the board and fix that series stuff from last week. Okay, guys, welcome back. Okay, the first thing, we had a question about series circuits. If one of those bulbs became either disconnected or just stopped working. Now, guys, remember, a bulb has a filament that connects the side of the bulb with the bottom of the bulb, and current goes through that filament and lights up as energy. So, what's really going on here? Well, if this 1 ohm bulb became disabled somehow, what would happen to the current in the circuit? There were 4 options. The current could go up, the current could go down, the current could stay the same, or the current could shut off altogether. No current would flow. And that's exactly what happens. As you guys will remember from our circuit master activity before we left school, if I have an opening or a break in that circuit, or if a bulb stops working, the entire circuit goes dead. So if this 1 ohm bulb dies or becomes disconnected, there's no current flow. I have current flow indicated by my green line here with an I right here. I also have 3 points designated, point A, point B, and point C. We're going to get used to those as we do the circuit combinations this week. So I want you to take particular care to notice where those points are. Okay, guys, that was the first question. So if a bulb burns out or is disconnected, there will be no further flow. What about the other questions? As more bulbs are added, so what I'm going to do is I'm going to connect bulb 1 again, and I'm going to draw in bulb 3. Bulb 3, I'm going to make that 3 ohms. 3 ohms. So I have a 1 ohm, a 2 ohm, and a 3 ohm. So instead of 2 bulbs having a total of 3 ohms, so the 2 bulbs together was 3 ohms. As more bulbs are added, this case, I added a 3 ohm. I've got a total of 6 ohms. So what happened by total resistance in the circuit? It went up. And as a result, if the resistance goes up, but your voltage stays the same, that would mean your current has to go down. Total current in this circuit must go down. And you can figure that out because by Ohm's law, if we had the 2 bulbs, 6 volts divided by 3 ohms total will give you 2 amps. So with 2 bulbs, there's 2 amps of current. With 3 bulbs and 6 ohms total, that means 6 volts divided by 3 ohms, 6 ohms, would give you 1 amp. So you can obviously see the current is going to go down in the series circuit if you add more bulbs. Okay? I hope that's okay, guys. Let's look at that parallel circuit now, again, before we do it in the lab. Okay, guys, let's look at those same 3 questions, but with a parallel instead. Remember, we introduced parallel circuits last week on Thursday. I have a 6 volt supply. It's powering a 1 ohm resistor and a 2 ohm resistor. But those resistors are not in the same branch. Here's my point A, and here's my point B. And you can see that the total current in green enters into point A. And from point A, the current splits into 2 different values. A blue current, which goes to the 1 ohm resistor, and a purple current, which goes to the 2 ohm resistor. Now you might also want to consider that the purple current, I have it listed as I through the 2 ohm resistor, plus the blue current, the current through the 1 ohm resistor, those 2 must add to the total current. This was one of our parallel rules on page 553 and also from last Thursday's video. So if the 2 currents must add together, let's take those questions then real quick from last Thursday's Google form. Well, let's apply them to a parallel instead. If one of those bulbs burns out, there would be a break in the line. It's as if a switch just turned off in the middle of that branch. But you can see, if that were the case, that the blue current would simply disappear. It wouldn't exist because no current can flow through a branch with a broken bulb or an open switch. This purple current would then equal the green current, but the green current would obviously change because there's less paths now. We only have 1 path to go through, not 2. Okay, so clearly, if we have a break in the line, the other bulb remains unaffected. Its branch is completely separate, still 2 ohms being supplied by 6 volts. Remember, 6 volts applied to each branch separately. That's the first thing we did Thursday, is we applied Ohm's law individually. So, how much current would be in the purple line? 6 volts divided by 2 ohms to give you 3 amps. So this current would be 3 amps. Now, let's put this line back in the circuit again. How much current is flowing in the upper line? Oops, that's supposed to be blue. Remember, we apply Ohm's law out of the gate individually. So 6 volts applied to 1 ohm, that's 6 amps. So how many total amps are in this circuit when both bulbs are working? Purple plus blue equals green. Therefore, 6 amps plus 3 amps is 9 amps. So what happens to the current when we lose this line? It simply goes from 9 amps down to 3 amps. The 6 amp line is no longer working. But the 6 volts of the power supply still applies between A and B, and it applies separately. Therefore, current The question is, as more bulbs are added to a parallel, the current should go up. Let's do that again. Let's add a third bulb, just like we did for our series. Let's make that bulb 3 ohms. Now I've got my blue and I've got my purple lines. Those are still working. If I take my 3 ohm resistor and I draw another line through there, let's draw that in pink, there would still be 6 volts because no matter what, from point A to point B, I can choose any of those routes to get from point A to point B. I apply Ohm's law separately. So how much current would be in this pink line down here? Think about it for a second. Apply Ohm's law separately. So 6 volts divided by 3 ohms would give you 2 amps. 2 amps in this line. What does that make our total current? It makes our total current 11 amps. So by adding resistors in parallel, we're actually making more paths for the current to travel. Total current goes up. Total current goes up. What happened to total resistance? Well, remember, guys, if our voltage stays the same and our current goes up, current goes up, voltage stays the same. That means resistance had to go down. Now, if we want to figure out what that is, let me show you this in a shortcut in just a moment. Okay, guys, this is a little bit tricky, so I really need you to pay attention. 3 bulbs in parallel. We're still using the 1 ohm, the 2 ohm, and the 3 ohm in different branches. Remember, they all get the same voltage. And we found that total current to be 11 amps. Okay. From page 556 in the small print, there's a unique formula addressing how to find equivalent resistance of resistors in parallel. And it goes like this. 1 over the equivalent resistor, or R total, is 1 over R1 plus 1 over R2 plus 1 over R3. If I take a common denominator between 1 over 1, 1 over 2, and 1 over 3, I'm going to get 6 because 1 and 2 and 3 all go into 6 evenly. Then, how many 1s are in the 6? There are 6 of those. How many 1/2 are there? There's 3 of those. How many thirds? 2/6. I just move everything into fractions. Then, I add the numerator and get 11. The denominator stays the same. So 11 over 6. But that equals 1 over R equivalent. In order to invert that, all I do is flip the top and the bottom. So REQ goes to the top, standing for R equivalent. R equivalent, or the resistance total, is 6/11 of an ohm. Now, why was it 6/11 of an ohm? Remember, we can always do Ohm's law with the totals. If you go back to the previous example, this can also be found using Ohm's law. V total equals I total times R total. So R total, or R equivalent, is V divided by I, where I'm using the total values. 6 volts divided by 11 amps, or 6/11 of an ohm. Very versatile, guys. You're going to need some practice on that. I encourage you to do that with some of the homework questions. We'll revisit this again tomorrow when we do a shortcut to this version, and we only have two resistors in parallel, and we can shorten that equation up a little bit. And we can do that multiple times. But for today, let's just use our resistance reduction formula for all resistors in parallel. 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R, etc., etc., etc. I could put as many resistors in there as I wanted to. Now, guys, I was going to show you the lab example too. I'll have to show you that tomorrow because we're running out of time a little bit today. I do want you to practice resistor reduction for parallel circuits. Go ahead and rewind this video if you have to, but let's make sure we get a good handle on how to find the equivalent resistor of multiple resistors in parallel. Now remember, this would mean if I was to take out those three resistors and create one resistor in its place that electrically did the same as all those three, that one resistor would be 6/11ths of an ohm. It was as if you redid the circuit by taking out the 1 ohm and the 2 ohm and 3 ohm and putting one equivalent resistor called 6/11ths of an ohm in its place. Concept's not that easy, guys, so I do need you to practice up a little bit. And I'll be with you tomorrow again to show you how this works, okay? All right, let's wrap up today. Okay, guys, now remember, the beauty of online education is that you can view this video multiple times and go through that example more than once if you're not sure how to work it. We'll do more examples in the coming days, but the benefit of doing online education is you can go at your own pace. So let's make sure we get a chance to review that example on how to find the resistance in parallel. And we can go back and answer that question. What happens as you add more bulbs in parallel? Well, remember, more branches means more current. So the current's going to go up. What does that mean about the resistance? Well, since the voltage stays the same, the resistance has to go down. And if one of those bulbs stops working, the other bulbs continuously light just like they did before. There's no impact whatsoever. Okay, guys, we'll have a little bit of practice on that. We'll go through some homework questions and we'll move on. Great times, and we'll see you tomorrow for another episode of Physics.